funny. Can you hear me now? Yeah, the power was off. Okay, so, all right. All right, so let's go over this one more time. So we went over the theory of Lagrange multipliers for inequality constraints. Equality constraints is virtually the same. And let's just do it one more time, because I want to pound this into your heads. I mean, in a midterm, you will be expected to recite this verbatim. Okay, so here's an optimization problem with equality constraints. Okay, and here's this Lagrangian. Now, does anybody, in this case of equality constraints, have I changed anything by tacking on lambda g of x? What I've done there is I've added 0 to the objective function. Okay, I could add 0 plus 0 plus 0. It's not going to change a thing. So that problem and that problem are the same. There's no difference. Nothing's changed. All right, you all agree with me? All right, and so the relaxation is just to kill that off. In this case, the equality constraints is a bit easier to see. With inequalities, you actually make things smaller with relaxation for sure. Right off the top, but here you don't. So it's a crazy thing to do, and it's amazing it works. Just to throw away the constraints you started with, and it's really a powerful trick. It comes up in a lot of unexpected places. All right, so all right. So anyway, then there's this relaxation. You see, the point is you do this for every lambda, and the equality constraint problem, lambda doesn't have to be positive. For inequalities, we assumed lambda was non-negative, and here lambda could be positive or negative. After all, it doesn't matter if lambda is positive or negative, right there. So we define this dual function, which is a function of lambda, and we optimize it for every lambda, which sounds like a lot of work. Before we only had one optimization problem. Now we have a family. So why are we bothering? And there's lots of good reasons, as we'll see. And so then basically, we know this because of the definition of relaxation. That for any lambda, going back here again, for any lambda, minimizing this will give you something less than or equal to minimizing that, because we have less constraints. So we can potentially go down further. All right. So the dual problem is to maximize this dual functional, which is always a concave function. So no matter how nasty the original one was, this dual functional is concave, which means in one dimension, its graph is a sad face. Okay, we want to maximize that. Okay, and that's known as the dual function. All right, and that's it. So that's what happens with equality constraints, and and that's it. So we're going to apply this right now. All right, so here's what's called the economic dispatch problem. And again, I hate the language. We're doing a resource allocation problem. We have a bunch of resources, different generators, and we want to know how much of each one we want, what level should each one be operating. The language economic dispatch is a corruption because of the real just obsession about economics in the power area. Sort of economic language is taken over. The control theorists just were kicked out of the room when a lot of the language and ideas came around. So it's basically we've got different generators that have limits on what the lower limit and upper limits can be. Now remember, we've solved the unit commitment problem. So these n generators all have to be operating. All right. So there's a hard constraint below, which is not 0. So we assume we've already solved the unit commitment problem, and now we're sitting how much, what level should each generator be operating at. All right. And that unit commitment problem is a whole other course. We won't get into that. I've got 100 generators. I've got 10 I want up, n equals 10. That's 100 choose 10 possibilities. It's a combinatorial nightmare. And you have to take a course in mixed integer programming. So in industrial engineering, we have the best department in the world for that. So go over there, go to industrial engineering. And there are all sorts of specialized algorithms for solving that. But it's not the hardest problem. So that problem at the balancing authorities, at like the ISOs, they don't find any trouble solving the unit commitment problem, even though it seems quite difficult. This they find much more difficult. All right, but let's solve it right now. Let's just crank this out. So I've got, again, a bunch of generators, and I've got this constraint that supply equals demand. All right, and that's the thing I want to relax. Okay, now there are other constraints that I could relax as well. But what's really valuable is relaxing that one constraint. So this is a design problem. Whenever you look at an optimization problem, you get a choice as to what you call S and what you relax. That set S was a constraint set that I didn't relax. Okay, so here we're going to relax that constraint, but not those. Now we could get inside with that too. Remember all the sensitivity ideas? We could find out the sensitivity to that upper bound. So it is useful to do that, and I might make you do it in the homework. I'm coming up with homework too right now. Right? All right. So there's the Lagrangian. So the Lagrangian is now G is my x, G is my vector that I'm trying to, my variable for optimization. And as always, I've got the objective function plus lambda times in this case, an equality constraint. In this case, G is that this has to be 0. Supply is demand. Supply equals demand. Supply equals demand. All right, that's it. So this is fun, because remember we did this last time. It was so cute. You see, this original optimization problem looks scary because of the coupling between the different variables. But this, when we try to minimize that, all the coupling goes away. That's why we love these tricks. Things like this are amazing. Well, so let's do it. So you write this out as a sum of terms like this, and that's what we call the Lagrangian decomposition. All right, so when we minimize this overall G, we actually get to minimize each one separately, subject to these inequality constraints. So the reason I gave you that really dumb homework problem, where the question was, so homework 2, I wanted you to minimize the function over x greater equal to 0. And I basically told you it was increasing. So there's no calculus involved. It's just 0. All right. Now the slope there, I told you, was not negative. Now if the slope had been negative, the function was increasing. I basically told you that. And so we know that you get a boundary point optimizer. And so I gave that homework problem just because last time we taught the course, a lot of people felt uncomfortable with boundary point optimizers. And so we're going to have to deal with that. But it's come on. it's one-dimensional. We can do this. All right, so if it's an interior point optimizer, then we can take derivatives, right? But in this case, it might not be. So here we have a G min and a G max. And our functions are going to be increasing. But I've got a lambda there, so it might not be. But it's possible that we can have f of gi minus lambda gi. It might be increasing as a function of gi. And so your optimizer would be down here at the bottom. Right? That's one possibility. All right. Now it's also possible if lambda is big enough that it's not increasing, and then you might get a happy face. So this is lambda small. But it's possible you could have a happy face, something like this, where you have an interior minimizer, not a boundary minimizer. And that's when you can apply calculus, assuming f is differentiable. All right? You can only apply calculus if you know the optimizers in the interior. All right? That was the reason for the homework. All right, so let's go do it. But what's beautiful here is that, so if all the optimizers are in the interior, so you can justify this, if it's a smooth function and everything, all the function, the f of gi minus lambda of gi all looks like that. So you optimize in the middle, Then all the slope here is 0, which says that the derivative, differentiate this, the marginal cost is lambda for every I. And that's the solution, right? So now we just have to interpret this graphically. Okay, so let's look at it. So let's first of all look at one case. So what's one generator, the solution for one problem. So we've got, you give me a lambda, I'm going to interpret it as a slope, all right? And we're going to see lambda's going to be positive. You tell me why in a minute. All right. All right, so lambda, or at least not negative. So I go around and I look at this function and where its derivative is lambda. So there it is. And I did this with Adobe Illustrator. I just drew a line and I moved the line. You know, I got my mouse on my Mac and I moved it until it touched and I found it graphically. Okay? That's it. So I don't need math. I need just to be able to move a line with a mouse on a computer. All right? All right. And so what happens when I make lambda larger? Well, as I move, if I make lambda larger, I'm sorry, I get a bigger slope to match up. I'm going to get a point which is larger. You know? Right? If I make lambda smaller, a shallower slope, I might end up going over here. And that's because of convexity. Convexity means that the derivative of f is or non-decreasing with lambda. You know? So bigger lambda means a bigger derivative. You know? All right. So you know, the G star is the optimizer. So as you increase lambda, the optimizer, it could stay the same or increases. All right. Now what about a fleet? We just do the same thing, right? There's no difference, right? Because remember, we've completely decoupled this problem. You've got n separate optimization problems. But let's look at it geometrically all at once. So I've got a bunch of cost curves for the different generators. And somebody gives me a lambda. There's this lambda just as before. But look what happens now. For this guy, this is really shallow. I look over here. It's never that slope. You know, I'd like to pick for F2 something up here, but I can't. All right? My trick doesn't work. So for this guy, for F3, I guess, or F4, if a couple of them I can do it, but for some I can't. So here's what you get. So yeah, so for F1 and F2, we never are able to match the slope of lambda. But for F3 and F4 we can. All right? So we're able to use calculus here and here, but here and here we have to use this trivial fact that this, you know, that f of gi minus lambda of gi is strictly increasing, which only happens if lambda is small. Or increasing anyway. All right? The fact that lambda is less than the derivative of f1 for, you know, for any possible g, and the same thing for f2. The derivative of f2 is always less than this. So we have that's critical. So we have the derivative with respect to let's say g at f of 1. Well, actually, I should say G in this region. That's why we know that this function, therefore, is increasing. And if you have an increasing function and you want to minimize it, well, you take the smallest possible value. Okay, that's all I'm saying. Right? And that's why you've got to do homework. You can't recite this crap. You have to do homework to understand it. You know, but that's how you do this graphically. I wanted to show it to you once. All right, so here we go. We've got our allocation. With this lambda, we have G1 is at its min, G2 is at its min, and G4 and G5 require calculus. So these guys are easy because they go to their lowest value. And yeah. And take a look, it's not what you might have guessed. I mean, the actual costs are very low, and yet you're not using them. You know, it's not obvious that you would want to shut down or put generators 2 and 1 at the lowest levels. Okay. All right. So again, before I said that we had that each of the GIs, as you increase lambda under convexity, as you increase lambda, the optimizer increased. Well, of course, that's true of the sum as well. And that suggests something, right, about how to solve this problem. Because we have a constraint, really, that supply has to be equal to demand. I'm solving this for every lambda, but there is a constraint. There is actually one lambda we care about, and that's actually the lambda where we do get feasibility. Supply equals demand. All right? Now, you know, this optimizes, you know, this gives you a solution. This minimizes Lagrangian, but it's not solving the problem. We're just computing the dual function for every lambda. All right. So anyway, so if you increase lambda, we're going to move the g's along, so the sum is going to increase. And this time, anybody shut off? No, we increase lambda so much that everybody's now an interior minimizer. And look how sensitive it is. I mean, you know, before G2 was practically shut off, and now it's only, you know, almost at full blast. You know, a little change in lambda and wham, you want this guy. And then if you make lambda really steep, is everybody on full blast? No, almost everybody. It looks like everybody but generator 4. And it's because his cost gets so steep at the end, you don't want him. Again, it's the marginal cost that's important, not the absolute cost. The absolute cost is the height here. It's irrelevant in these calculations. I could take this curve and shoot it up as high as you want, and I get the same solution. That's really surprising. You know, I mean, that's really weird. You've got something that costs a fortune, and you're going to use it. It's has to the unit commitment problem. So if I added a huge constant times this, I wouldn't have committed it in the first place. You know, I wouldn't have allowed it in. All right. So basically, so I'm solving the dual problem, and really, remember, we're trying to maximize the dual, but equivalent, we're trying to get feasibility. We're trying to choose a lambda so we have feasibility. It's the same thing, as it turns out. And what you can do then is just, you know, start in the beginning, take lambda equals 0, which would mean shutting down everybody, taking everybody to the minimum, you know. And that would clearly be, if everybody's at their minimum, that demand had better be bigger than that. Otherwise, the problem is not feasible. All right. All right. So you with lambda equals 0, everybody would be at their minimum, from what we saw before, and you gradually increase lambda until you get a match. So as you increase lambda, this gets bigger and bigger and bigger until finally this is equal to the demand D, and you're done. That's it. All right. All right. You got me? Are you with me? So that's a graphical way of doing it. Of course, there are algorithms. I mean, this leads to algorithms, and I don't know how much detail we'll get into that, but we will talk about how to write code for this. But I don't know. It seems to me that you should really just take a course for that, because you can take this and plug it into MATLAB and solve it. And the theory is really nice, but that's a whole course. So I don't think we can say much about algorithms. You know. All right. So what about sensitivity? So remember, when we had a family of optimization problems, you know, I'll remind you. This beautiful result. You know, so basically if I relax the constraint, you know, so as I let C get bigger and bigger, I have a larger and larger set. So, and there's a minus sign missing, isn't there? As I let C get larger and larger and larger, I get a bigger and bigger constraint set. And so we know that this minimum is going to go down, you know. So the lambda star was, that's less than or equal to 0. So basically the sensitivity to the constraints is the derivative here. So we can look at the sensitivity to the constraint that supply equals demand. If the demand is increased a bit, how much more will I have to pay? And I'm going to check my notes because it's either lambda or minus lambda. Well, let's see if it makes sense, okay? Because we know lambda is positive. Oh, good, yeah. So in this case, I'm sorry. See, you have to check the formulas, but you can also use your intuition. Like, how did I correct my mistake here? I remembered that this was a decreasing function of C. So I know this has to be non-positive. Same thing here. If I make the demand bigger, you can expect your costs to go up. All right. So lambda, in this case, we saw was positive. You know, so we have this this constraint. So that's what happens. And so if you go back to look at this energy information agency plot that was showing this hypothetical dispatch curve for the summer of 2011, if you had a low demand, which in this case would be 67 gigawatts, so it's not very low, you get one slope. And when it gets really big, you get another slope. Like here, here the slope, you know, is quite shallow, and here it's quite steep. It might be a tenfold difference, and that's one explanation for the way prices go up and down, you know, in regions. It's basically, you know, initially you're dispatching cheap units like these combined cycle natural gas plants that are very efficient, very, you know, have fantastic heat rates, and eventually we have what they call marginal cost of natural gas other. I have no idea what that is, but it's something that can be brought online quickly and is expensive as hell. So it's got a much bigger slope. But that range of prices is only like tenfold. You know, if you actually look at what goes on in these markets, it's 1,000-fold. And why on earth would that be? You know, that's a question we'd love to answer. Well, maybe we'll try to figure it out by the end of the lecture, of course. I don't know. All right. Okay. So we get that as well. So we get the if the demand goes up a little bit, how much more will I have to pay? Which is something they really do want to know, because they're solving this problem every 5 minutes, you know, and they want to know what, if the demand goes up a bit, how much more we'll have to pay. All right. All clear? All right. Transmission constraints. What do you think will happen now? So basically now I've got two zones, and I've got a transmission line between them, and it's subject to constraints, you know. And they're not really hard constraints, but by policy they're hard constraints. You know, there's a constraint that only so many you know, megawatts can flow through this line, and really they could be violated by double in practice. And maybe after an hour they'd heat up and collapse. So there are policy rules that create this, and that causes strange problems. And you can see why as we go along. So we had this problem before. We had that we want to minimize cost, so just supply equals demand. But now we've got an extra constraint right there, and we have a flow across the transmission line, which is the generation. So if the generation in zone 1 equals the demand in zone 1, then this is just like its own little universe, and it just sits there. The transmission line doesn't have to do anything. If this is bigger than this, there's going to have to be a flow, you know, because that power has to go somewhere, so it goes through the transmission line. And we can make the same argument there. So this is the negative of this. And both of these, and this is the flow, whether it's positive or negative. So positive means there's excess generation in zone 1, you know, and if this is negative, then the flow is that way. And the constraint is bidirectional. Right? So we have an absolute value. So we have that this difference is less than some p max and greater equal to some minus p max. Depending, the two cases, flow going that way or flow going the other direction. All right. So what are we going to do? It shouldn't be hard, right? Are we going to get as lucky as we were before? Well, I get sick of going through PowerPoint slides, so let's think about this on a blackboard. Okay. Okay, so so we're going to have, what are we going to, so you tell me though. So I've got this minimization. As I started before, but now I've got this constraint, which I'll write down. And that's going to be less than or equal to the demand in zone 1. I'll write that as this D1. And then plus this P max. All right. And then I've got that other annoying constraint. And so how would I do this? I always want to make this into less than equal to sign. So let's bring this over here and that over there. Is that algebra okay? Just as a minus sign right there. So you all tell me, what am I going to do? Well, I know that I'm going to want to relax this, and you have to think about how I'm going to do it. Actually, it might be more fun to play with that. I just realized it'll be much, much prettier if we do that. I just don't remember. We're going to go through this in depth next time. But so, what would you do if you were given this problem right now?
Cry.
What? Why? But it's so much fun. I mean, you agree that this was pretty, how everything fell apart. So these are the same, by the way, right? I mean, these were the fact that these are equal is just the first constraint, that supply equals demand, All right. You bring this over to the other side, and you get the total generation minus the total demand, okay? So this constraint was already there. It's only written this way to stress what the flow means, okay? Come on, what would you do? I mean, you would not cry.
Do you need to pick one to pick a constraint to relax?
Yeah, well, if you picked one constraint to relax, then you would cry. Because if you say, did what we did before, and we took this up here, let's do it. So when I'm doing this, I'm relaxing, right? Okay, so if I did that, then I'd be minimizing something, but then I'd have coupling constraints again. So what was so beautiful before is that I was able to decouple the problem. So the only way to decouple the problem is to introduce both of these, relax everything. So you've got to go through and you've got to ax this out, you've got to ax everything out. So you have to put in some brackets here, because there's going to be a lot of terms. So we've got that. Well, no, put the brackets outside. So we'll put a
Professor, just for clarification,
yeah,
those two summations, I guess,
yeah.
the GI and the GD, those,
Yeah.
those are transmission constraints, right?
What's that?
Those are transmission constraints?
Yes, that right there.
Right.
Yeah, that, all I'm doing is rewriting that. You know, when I say G zone 1, I'm writing down what I mean. It's a summation of all the generators in that zone, you know. And again, that was the flow. If this is positive, it's the flow going from there to there. All right. So we ax that out. Again, we'll do this again next time in detail. We have a Lagrange multiplier for this. Let's give it another name. I've forgotten what I call it in the slides, but let's call it gamma plus. That's a gamma. And we stick that in, right? And that's positive. So I get rid of that constraint, and I put in with relaxation, where this gamma plus is going to be greater or equal to 0. All right? And then I go through and I have this last one. I'll call it gamma minus. It's also greater or equal to 0, because we have an inequality constraint. And that was an I, wasn't it? So that's gone as well. And that minimum, put a bracket here, that would be my dual functional that the function I defined before. But now it's a function of 3 variables. So it's a function of lambda for supply and demand, and it's a function of gamma plus, and it's a function of gamma minus. So it's a function of 3 variables, and that's the dual is to maximize that. All right. Now that looks bad, doesn't it? I mean, I'm creating a monster now. I've got this thing I don't know and I want to maximize it. But look at this thing. It's beautiful. So it might be that I don't know what the hell this is. But this is, if you can't see this is beautiful, you're crazy. You really have to see a therapist. Okay, so you've all got that imprinted in your brains, all right? We've got 2 zones, and there's a constraint between them. And let's remember reality here, okay? So this could be the Midwest. That could be Minnesota, where the wind is blowing. There's tons of wind energy. Power is free, okay? And it typically happens in the Midwest. There's a transmission line to Missouri, and all they've got is some crappy coal generators. Okay, so they want that power from that cheap power, but this is binding. That's what happens every day in the Midwest. Okay, so the prices here will be very cheap, but here they could be very expensive because they can't get the cheap power. And we just saw the price is marginal cost, and if they're still using we haven't seen that. And prices will be marginal cost. It's those expensive units that determine the cost here, and I forget, that's right, I'm jumping way ahead. Those Lagrange multipliers are prices. In a market, we're going to find that out. I'm jumping way ahead. I'm jumping weeks ahead. But anyway, it's good to say it way in advance. The reason you get cheap prices in one place and expensive prices in another is because it's the most expensive unit that determines the price. That's what we'll see. So keep that in your brains. Let's turn that off. Yeah.
Here it's saying that gamma minus greater than or equal to 0. So then shouldn't be less than or equal to 0?
No. Less than. Remember, this is non-positive. Okay, this could be negative, and for this to be relaxation, I need a coefficient that is greater than or equal to 0. So the product is less than or equal to 0, and that's why it's a relaxation. So I've introduced something that's less than or equal to 0 for any feasible solution. So when I minimize over all G, put a vector there, I have no constraints here, except, well, I do have the min and max constraints. Forget that for the moment. I have relaxed constraints, and so, yeah, again, for feasible G, that is non-positive, that is non-positive. So I've added something that's potentially could reduce the overall value. Okay, so if it generates in zone 1, so I want to solve this now. What I want to find what this dual function is, okay? Which means I have to solve this optimization problem. But it decouples, right? I mean, I've got, if I take a particular I'm going to say, well, let's look at a case where it's in zone 1. It appears here, so there's an f of I of gi I have to worry about. There's a lambda times gi I have to worry about. Okay, so anything constant, I want to move outside. It doesn't affect my problem. And then I'm in zone 1, so I've got it's over here, and so I've got a gamma plus I have to worry about. And of course, then there's also the gamma plus times this business here. And I just realized we really should put Roman numerals here. I didn't realize that looks like demand. I mean, just make sure it's a zone, not a individual, not demand for one generator. There isn't one individual wants a particular generator.
So what are you writing on the bottom right there?
The things that aren't variables. Oh. So I've got a lambda d, doesn't depend on g, take it outside. And the same thing here, I've got, those are constants, they're just given. So I'm trying to minimize this, the ith optimization problem is like given right there. And so we see that basically we get the same solution as before. So if it's an interior, if the optimizer and assume everything's smooth, you know, and everything is differentiable. You know, so the same setting as before, okay? And then I can just take derivative set equal to 0. And I get the marginal cost, the derivative of this, the derivative of this is 0. Okay, so I don't want to have to, this is in brackets, I don't want to have to write it down again. So this thing, if it's an interior optimizer, we can apply calculus, not calc 3, calc 1. All right, and this thing is going to have derivative 0 at its minimum. You know, happy face, the bottom of the happy face, slope is 0. And so when you solve that, the derivative of this is lambda minus lambda, the derivative of that is gamma plus. Okay, exactly the same thing as before. There you have it. So this is for any generator in zone 1. It doesn't matter which one. Everyone has the same marginal cost. That's just in zone 1. And if gamma plus is, gamma plus could be positive, it means there's a huge gamma plus. If gamma plus is positive, it means it's positive sensitivity to this constraint. It means you've hit the max. So it means there's way more generation than demand, you know. And if these can be interpreted as prices, as we can imagine, then with the price, the price drops because the demand is so low. Yeah. Yeah.
Repeat that one more time.
So we will see that these Lagrange multipliers correspond to prices, and we see that because the demand was so low, the price dropped. That's one interpretation.
About being positive?
What's that?
The multiplier, if it's positive?
Well, it always is. For inequality constraints, we always have positivity. Yeah, for these guys. And so it's just a matter of, this could be 0. This will be 0 if the constraint's not binding, because the sensitivity is 0. Yeah.
What is the dash over here in the differential?
Where?
On the bottom left, the dash in between the brackets.
Oh, I decided I didn't have to rewrite all that. That is just all that. When I'm trying to minimize a function and it's smooth and I know the optimizer's in the middle, in the interior, I can use calculus. All right. All right. So so it's not any harder really than we had before. It's just that in each zone, there's an equal marginal cost. And then we can use the same geometric method I mentioned before. Basically, make sure that everybody can match this slope. And of course, there are the boundary issues that I mentioned before. There's no issue, no differences at all. All right? Trivial? Some of you aren't on board. Almost done. Well, ask questions, all right? Come next time. Yeah, Neil. Yeah.
Confused about how before we were talking about finding the maximum of a dual, now we're finding the minimum of this.
No, I'm just trying to find the dual. So basically, I want to construct the dual function. Yeah, I have to minimize this for every lambda, gamma plus, gamma minus, right? But see, the only point is I get the structure of the optimal solution like that, you know? I mean, see, that's the thing is that it looks really scary. I've got to solve this maximization. Well, I never really do. Because once I get this structure, once I know that the solution is that the marginal cost for every generator is the same in every zone, that's basically a solution. You know, I basically then move the lambdas around until I make sure that supply equals demand, and I'm done. Because I know the structure of the optimal solution. That's what's so awesome here. It's the insight, you know. You know, if I just gave you an answer without any insight, who cares? You know, the fact that marginal costs are equal, that's it.
Another question, I'm sorry.
Yeah.
So if that's the differential of
This, yeah.
right there, why do you have lambda minus gamma plus
Oh,
instead of minus lambda
no,
plus gamma?
the derivative of this is equal to 0, right?
Oh,
Yeah. So all I did is I took the derivative of this with respect to GI is this lambda. The derivative with respect to the GI is this gamma plus. So I just brought it to the other side.
I got you.
Yeah,
Okay.
you know, just like before. All right. So that's it. You know, I mean, it's.
Yeah, actually, I remember.
Yeah.
Should that mean, you said GI equals GI's asterisk? Or do you have to,
Oh yeah, this is at the optimizer. Yeah. I should say, well, yeah, put a space there. Evaluate at the optimizer.
Right.
Yeah. The decision we make, the amount of generation is going to be such that again, subject to this constraint, everybody's going to be set so that their marginal costs are the same. You know. Now again, this is before. If this is small enough, then it's got to be operating as minimum. And if this is huge, it might be operated as max, because the boundary optimizers we have to worry about separately. But to the fact that you can get the structure of the solution without thinking, you know, this notion of a Lagrangian decomposition is so powerful. And the fact that it's really so simple is the reason I emphasize it so much. Right? So we're going to develop this some more, and soon get into the economic implications. Okay, but that's it for today. And yeah.